Hey guys, this is Dr. Mans, and in this screencast, I want to talk to you about something called intramolecular attractions. And this is basically just what keeps two atoms stuck together. And specifically, we're getting into covalent bonds. There are two types, nonpolar and polar. You need to know the difference between these two things, And with polar covalent bonds, there's some special stuff that goes on, mostly having to do with water and hydrogen bonds, but we will get to that later.
So the first one we're going to get into is a covalent bond. And here we have two hydrogen atoms. Remember, their atomic number is equal to 1. So that means each of these has one electron. So here's the nucleus. There's one proton. And there's an electron out here that's zipping around this orbital. Same thing for this guy. There's one electron over here zipping around this orbital. And as they get closer together, you're going to notice that this orbital, this cloud, is changing shapes because this electrical negative charge is getting pulled towards this positive nucleus. And the same thing is happening here. This negatively charged cloud is getting pulled over here towards this positively charged nucleus. And as they get close enough together, those electrons can start swapping places as to which side they're going to be on. And this is a bond. So what's going on right here is that these two atoms, these two nuclei, are stuck together. Why are they stuck? Well, because there's a negatively charged cloud over here that's going to be attracted to the positively charged nucleus. And the same thing holds true for this nucleus being attracted to that negatively charged cloud. And so for that reason, they're stuck together. And those electrons just can swap places. Now, this is a pure covalent bond. That means there's absolutely equal sharing. That means one of these atoms is not hogging the electron. They're spending half their time on one side, and those electrons are spending half their time on the other side. There's a 50-50 split.
So now let's take a look at what this actually might look like if you were to try to picture this in your head, okay? So two hydrogen atoms come together, and you can see those electrons are zooming around those 1s orbitals. And as they get closer, now they can actually start sharing those electrons. So now, this is a covalent bond. It's a single covalent bond also. Single covalent bond because they're sharing one electron between them, okay? So this hydrogen atom donates one electron, and this hydrogen atom donates one electron, so therefore it's a single covalent bond. Now, let's get a little more complicated. Okay, so this is a double covalent bond. So now you can see in purple, these two oxygens are each contributing 2 electrons. 2 electrons. So that's a double covalent bond. And then you want to talk about a triple covalent bond. Here we have two nitrogen atoms, and they're each contributing 3 electrons. 3 electrons. So that's kind of what it looks like if you're going to visualize what's happening. As these electrons are swapping places between the atoms, and not only that, but they are sharing them equally. So this is what's called a non-polar covalent bond. Again, non-polar covalent bond. Okay, so now let's get into what's called a polar covalent bond. What is that? How do you make one? So first of all, it's not always a 50-50 split as far as where the electrons spend their time in a covalent bond. So they can attract electrons to varying degrees. And by they, I mean the two atoms that are in the bond. So we can define how strongly an atom is going to attract electrons by a word called electronegativity. So that is basically how strongly does it attract electrons while it's forming a bond. So if it pulls electrons really strongly, it's more electronegative. If it's not very electronegative, then it doesn't pull electrons strongly at all. So for instance, if we've got hydrogen hydrogen bound together. This is a non-polar covalent bond. So that means they share the electrons equally. So neither one of them is what I would say is extremely electronegative. So not electronegative. Or not strongly electronegative. Okay? Now let's get into what happens when you have one that is strongly electronegative. So here's a picture of a water molecule, and here's oxygen bound to 2 hydrogen atoms. A covalent bond joins oxygen to hydrogen here, and oxygen to hydrogen here. Now what are these blue arrows all about? This is saying that oxygen is extremely electronegative. So what that means is that they are not sharing the electrons evenly in this bond here. Oxygen is actually hogging them. They're spending more time with oxygen. Oxygen, nitrogen, and fluorine are typically known as strongly electronegative atoms. So the reason we care so much about polar covalent bonds is that they create what is called a permanent dipole. Notice I said permanent. This is in contrast to something like a London dispersion force, which is caused by a temporary dipole. So a dipole is just a fancy way of saying that there's partial charges on one side of a bond versus the other. So let's take a look here. So we have hydrogen bonded to oxygen. Right? So there's a bond right here. Now, as you know, oxygen is highly electronegative. That means that the electrons spend more time with oxygen. This is a partially negatively charged oxygen because of that, and hydrogen is partially positively charged, so this is a dipole. This side of the bond is different than that side. It's very polar. That's why it's called a polar covalent bond. And the same thing is true for this other side. There's a partial charge on the hydrogen. So because of this polar covalent bond, we now have what's called a permanent dipole. And this is going to be kind of a big deal because it will allow things like hydrogen bonding to occur. All right, let's sum this all up. So covalent bonds exist due to the sharing of valence electrons. In a non-polar covalent bond, they are shared equally. In a polar covalent bond, the electrons are shared unequally. They do not share equally. That is because one of the atoms that is involved in the bond is strongly electronegative. It hogs electrons. Oxygen, fluorine, and nitrogen are 3 atoms that you need to know as strongly electronegative. So if you see these things in your head, you need to automatically think polar covalent bond. As soon as you see those, you should think that it might be forming a polar covalent bond. Now, because of this unequal sharing of electrons that occurs during a polar covalent bond, you're going to have what's called a permanent dipole. And that means you're going to have partial charges on either side of the molecule. So if we wanted to talk about this stuff in terms of the strength of attraction between atoms or molecules, and if we have all of the weak attractions down here on the left, and all of those strong attractions over here on the right, we would put hydrophobic interactions way on the left. These are going to be due to temporary dipoles. We would put covalent bonds way down here on the right. Because those are actually pretty darn strong. Now what about this thing about a permanent dipole? When we talked about polar covalent bonds causing partial charges. These are permanent partial charges. They're still pretty dang weak, but they're stronger than this hydrophobic stuff. So we would put them maybe right here. So here we could put permanent dipole. All right, that's it for today. Thank you.